Okay, everybody, welcome to the very last lecture. Thank you for sticking it out to the end. So I'm going to present you with a practical problem here. Now, this is something you're probably better off not knowing, but when you fly across the Atlantic, your plane is assigned an altitude, and based in thousands of feet. So even thousands of feet are planes going east, odd thousands of feet are going west. And so if you go 32,000 feet, then you're going in the same direction as someone going 30,000 feet, and the opposite from 31,000 feet. Now, usually, this is done with an air traffic control tower. Some centralized person does this. But imagine that because of budget cuts and deficits and so on, the European Union and North American whatever decide to eliminate centralized air traffic control. And they say, well, that's no problem. Let the airplanes decide among themselves. So we can hire high-paid consultants like Hagit to advise us on robust algorithms for assigning unique altitudes. So the idea is everybody starts out with a unique ID, which is their flight number, which is taken from a very large namespace. And you want to choose a unique altitude. And the question is here, if you pick your own altitude, how many choices do you need in order to make a fault-tolerant, weight-free air traffic control system? So this problem is typically called the renaming problem, because one way to think of it is you want to translate your long name into a short name, which is which altitude you're taking. Now, you can imagine trivial solutions where if IDs come from a small namespace, you might just pick that slot. So instead, we're going to require that the protocol is anonymous, meaning that it doesn't depend on who you are. In particular, because we want to have, there's some technicalities. We want the processes to communicate with shared memory. They should have IDs and things like that. So what we'll say is that your output depends on your input name. So you're allowed to use your input name and the interleaving, but not your ID. So if you're process 2, you're not allowed to use the fact that you're process 2 to pick your output. But you are allowed to use the fact that you're LL235. Okay, and this is a restriction on the protocol, not a restriction on the task. So this says that we only want solutions that have this problem, but it doesn't say anything about the task itself. So what I'm going to do is I'm going to give you an upper bound, that is a renaming algorithm where for n+1 processes we have 2 n names. Then I'm going to do a lower bound and show you that under certain conditions, this is the best you can do. There's some matching upper bounds that we're not going to do, but I'll mention at the end. So first we'll do a renaming with a 2 n name. So here is a shared memory weight-free algorithm for doing renaming. And I hope Hagit won't be annoyed by this, because this is her algorithm. So we start out. The idea here is we have a shared memory, and I'm going to kind of abstract over all of the details and just say, you pick out, everybody has an input name, which is your flight number, an output name, which is the altitude. And we'll start out by saying, well, everybody starts out and they pick output name 0. I guess that means that you get towed along the ground in your airplane. And so then you claim that, which means you write this pair to a shared memory. So you announce to everyone, hi, I'm Algebraic 227, and I want this elevation. And then you take a snapshot of everyone's claims. So you see what everyone else wants. Then what you do is you say, well, are there any conflicts? In other words, did anybody else claim the same output name that I claimed? And if no, then I'm done. So I stop and I take the output name that I wanted. Otherwise, if there is a problem, then what I do is I look at all of the input names that have been announced, and I pick my rank among them. Then I take that rank and I find the unclaimed output of that rank. So if I'm number 2, then I find the second name that nobody's tried to claim, and then I pick that, and then I go back and I try to claim that. So I repeatedly announce a claim. If there's a conflict, then I back off, pick my rank among everyone who's who's made an announcement. I pick the blank, the unclaimed slot of that rank, and then I keep doing this. So this is a fairly simple algorithm.
What is your rank?
Your rank is you look at all of the IDs that have been written, including yours, and your rank is 0 if you're the lowest. Your rank is 1 if there's one that's lower than you, and 2 if you're lower than that. So first, to claim that everybody chooses a unique output name. We don't have 2 airplanes flying at the same altitude. And that's fairly simple because imagine that you have 2 processes that both claim the same name, and they both halt with that. Well, what happened is that they're going to announce it to the world and then leave it there because they halt. But after you announce, you take a snapshot to check. And the second one to write is going to see that there's a problem. So that can't happen. So if they do choose names, we know that the names must be unique, because you're not going to stop until you see that there's no conflict. Next claim, and there's a subtle point here. If the number of participating processes, not the maximum number, but the number that actually show up, is m, then, actually, sorry, that should be m plus 1. The output names are going to be in the range 0 to 2m. So the range of names that are announced are going to depend on the actual number of participants, not on the worst case behavior, because we're going to use this fact later on. So the proof here is that any time a particular process takes a snapshot, since their m is eventually a participant, it's going to see fewer, less than or equal to m output names claimed by others. Its input name has got to have rank less than or equal to m, because there are only m processes. So when it tries to claim something, it's going to claim, it's never going to claim a name that's higher than 2m, because it will always find enough unclaimed names below 2m. So if it does choose a name, it's going to be in this range here. So finally, we claim that the protocol is weight-free. That is, every non-faulty process always finishes. And the answer is, well, first off, there's obviously no waiting. Nobody is spinning waiting for everyone else. So the only possibility is that you run forever, always encountering conflicts. And I'm going to gloss over some of the details a little bit here, but let's assume, by way of contradiction, that this runs forever. There's some scenario where some number of processes fight forever trying to grab names. So then you consider the active process with the lowest rank. And the claim is that eventually everybody else will keep trying to claim higher values than that. There's a set of values that are permanently claimed. All the output names have been announced. So at some point, everybody's rank stabilizes. And then nobody, if you look at the lowest process with the lowest rank, nobody's going to compete with it. It's going to terminate, and then you do the same argument again. OK, so that says we have n plus 1 processes, and names in the range 0 to 2n. So next question is, can we do better? And so now we're going to say, well, we'll call this hard renaming, because it's harder than the renaming that we know how to do. And we'll say, under what circumstances, if we have n plus 1 processes, can we get away with using 2n names? For example, if we have 3 processes, is there an algorithm for 4 names? And what I'm going to do is I'm going to show you some circumstances under which this problem can't be solved, and then allude to some results showing that there are circumstances when it can be solved. So first thing we're going to do is I'm going to reduce this to a much simpler problem called the weak symmetry breaking. And this is useful because it's a simpler problem and we can fit pictures onto slides, whereas with renaming that can be awkward. So weak symmetry breaking, in fact, we looked at this problem early on in the course, when we were looking at separation results. You can think of this as a black box where every process shows up. It has a fixed input. You don't get to choose your input, you just show up. And what happens is you get back either a 0 or a 1. And the rule is that if all the processes participate, if all n plus 1 show up, then at least one process gets a 0 and one process gets a 1. So it's a very weak requirement. It's called symmetry breaking, obviously, because you can divide them up into two groups. Then if fewer participate, then we don't care. So if only 2 out of 3 show up, it's OK if everybody gets a 0. So this is a fairly weak kind of requirement. Now the basic observation here, though, is that weak symmetry breaking is equivalent to hard renaming. So that if I can solve weak symmetry breaking, I can solve hard renaming and vice versa. And so that means that if I have a lower bound for weak symmetry breaking, then I have a lower bound for hard renaming. And the other way around, if I have an algorithm, then I have an upper bound as well. So let's show you how to do the reduction is very simple. So I'm going to show that if I have a weak symmetry breaking black box, then I can solve the hard instance of renaming. And so the idea is each of the processes shows up into the weak symmetry breaking box, and they come out in either group 1 or either group 0 or group 1. So now what I'm going to do is I'm going to take 2 renaming algorithms and wire them to the 2 groups. And the trick is that this one here, I'm going to do renaming starting from 0 moving up. So if Q plus 1 processes pop out here, then I'm going to do renaming from 0 to do Q using the algorithm that I showed you before. This one I'm going to use the same algorithm, except I'm going to move down from 2n minus 1. So instead of moving up, I'm going to move down. You can think of this as solving regular renaming, then subtracting the result from 2n minus 1.
Q is the number of processes.
Yeah, Q is the number of processes that come out on this side. Actually, I think Q plus 1 is the number. And so whatever this value is, these ranges don't overlap. You don't know Q, but you don't need to know Q, because what happens is you're picking, this is why it's important that the renaming protocol that we did before, the highest name chosen depends on the participants, not the worst case number of participants. So the actual number of participants here is Q plus 1. And so the highest name that can possibly be assigned is 2Q. And this is the symmetric case. So so you get n minus q plus 1, n minus q. Everyone that doesn't show up here shows up here.
So you use a specific renaming, a specific adaptive renaming algorithm?
Yeah. In fact, we used the one that I showed you on the previous slide.
Because not every renaming algorithm is adaptive.
Yeah. So it has to be an adaptive algorithm. But the flowchart I showed you before works perfectly well. So we take 2 copies of that, and then just reverse the outputs on one of them. So that one direction we're choosing names going this way, the other one we're choosing names going that way. And the hard part is basically to split the processes so that they move into separate pieces. So I claim that if I have weak symmetry breaking, and then this is the sort of regular easy renaming, and this we can do with read-write registers, then I can solve the hard renaming problem. So in some sense, the hard part about renaming is symmetry breaking. It's not actually assigning the names. And the important thing, again, is that we don't know in advance what Q is, but whatever it is dynamically, the highest name issued over here is going to be less than the lowest name issued over here. So there are no duplicates. So this, by the way, is not an adaptive hard renaming. So we lose the adaptiveness. So it's possible that only 2 processes show up, and then but somebody picks 2n minus 2. So we can go the other way. So here is a hard renaming instance. 3 processes come in. This one takes name 3. This one takes 1. This one takes 0. So we have 3 processes, 4 possible names. And now I'm going to show you how to do a weak symmetry breaking. Well, the answer is I just put a little box on it that takes the name mod 2. And because they can't all be 0 and they can't all be 1 because there aren't enough even numbers and there aren't enough odd numbers in the range there. So that's a way of going from hard renaming to weak symmetry breaking. So you can see we can go back and forth between these two problems. And weak symmetry breaking has, since it has only binary outputs, it's easier to deal with. Okay, so here is the strategy that we're going to use. I'm going to assume, by way of contradiction, that I have a weight-free read-write protocol for hard renaming. Now, remember from the proof of our earlier fundamental theorem that if there is a weight-free read-write protocol, then we can, then there is one that uses the iterated immediate snapshots. And the protocol complex for the iterated immediate snapshot is simply standard chromatic subdivision iterated. In the picture, I've only done it once because I'm too lazy to draw, hundreds of little simplexes. But you should think of this as being further subdivided, big N times. And so this is the protocol complex for what we claim is the solution to hard renaming. I'm going to use 0 to represent, white to represent 0 and black to represent 1. And so if you look at the output value, that's a black and white coloring, or binary coloring of this complex. So whereas before with the set agreement we had multiple colors, here we're going back to the 1950s and only using black and white. So we have a black and white coloring of this weight-free read-write protocol complex. Now the next thing to notice is that, well, remember we said it's anonymous, which means that things can depend on your input name but not on anything else. This translates into a requirement that you have to be symmetric on the boundary. Because a subset execution here would look just like a subset execution there because you're not allowed to use explicit IDs. So we have a black and white coloring here that's symmetric on the boundary of the simplex. And finally, weak symmetry breaking, remember, says that somebody has to get 0 and somebody has to get 1. That means that there are no monochromatic simplexes. There's no simplex whose vertices are all white or all black. So we have a collection of conditions here. So we have this complex that's an iterated chromatic subdivision. And it makes it easier because we know exactly what this complex looks like. We don't have to deal with arbitrary complexes. We can deal with this specific one. It's a black and white coloring. It's symmetric on the boundary. And I haven't defined exactly what symmetric means, but I'll do that later. And it's done in such a way that there are no monochromatic n simplexes. And the question we want to ask is, when is that possible? So we need something like Sperner's lemma. Remember, Sperner's lemma said that if you had a subdivided complex that's colored with n colors with conditions on the boundary, then some interior simplex had to have n color, had to be properly colored. And so what I want to do is say something to the effect of, well, if we have a subdivided simplex, black and white coloring, symmetric on the edges, then there must be a monochromatic simplex and simplex in the middle, kind of analogous to a Sperner's lemma. And what we'll see is that we can do this sometimes. So this won't be quite as satisfying as Sperner's lemma, which holds all the time. I'm going to give you something that only holds part of the time. Okay, so to get there, so we need a combinatorial result that is sort of the analog of Sperner's lemma. So this is the black and white version of Sperner's lemma. It's called the Index Lemma. So we'll start out with the simplex. Now, first thing I want to do is I want to orient the simplex. So the orientation of a simplex is I take each of the vertexes and I write them down in some order. And I take all the even permutations of that order. So an even permutation is, you know what a permutation is. An even permutation is one where I start out with one order, and then by flipping adjacent elements, that's a transpose, and if I do that an even number of times, it's an even permutation. So every permutation is either even or odd. So that says that every oriented simplex has two possible orientations. So I can, in this case, I have a clockwise orientation, so I go yellow, blue, and red, which is a clockwise orientation. Or I could do it the other way around and say yellow, red, and blue. And these are odd permutations of one another. So they're different orientations. So if I have an orientation on a simplex, that induces an orientation on the edges. So here I have a clockwise orientation, and that takes this edge and orients it this way, and that way. And there's a formula for writing this down, but I'm not going to do that. You can use your intuition just to think about what it means to orient. You can think of an oriented edge as an arrow and an oriented simplex as a either clockwise or counterclockwise. In higher dimensions, you're on your own. You know, I mean, the way to think about, for 3 dimensions, the way to think about it is left hand or right hand. You know, you have left hand rule or right hand rule. You know, there's a dozen different mathematical ways of defining it. You know, you take a set of coordinate axes, and two coordinate axes have the same orientation. If the matrix that carries one to the other has a positive determinant, it's opposite if it's a negative determinant. You know, all kinds of ways. But for our purposes, your intuition will do what you want. So we'll talk about an oriented n-manifold with boundary. So this is a manifold with boundary. Every triangle, every edge here is a face of either 2 or 1 triangles. Every n-1 simplex is a face of either 1 or 2 n simplexes. And I'm going to put an orientation on each one of these with the property that if I look at the induced orientation on each common edge, that they cancel. And so this is an oriented simplex. Sometimes it's called the coherently oriented simplex. Sorry, complex. But the idea is that I have adjacent n simplexes induce opposite orientations on the common face. Now, not every manifold is orientable. So it's not always possible to do this. For example, on a Mobius strip or on a projective space, these are non-orientable manifolds, and you cannot do this. But on subdivided simplexes, which is what we really care about, you can always do that. So that's always orientable. So all the complexes that we're going to worry about are orientable. Okay, so given an oriented n-manifold with a boundary, I'm now going to put a coloring on it. Now, this is unlike the process ID coloring, which we use most of the time, where every triangle has 3 colors. Every n simplex has n plus 1 colors. This is an arbitrary coloring. There are most n colors, but we scatter them around in any kind of arbitrary way. So not every triangle is properly colored here. But I'm interested in counting the number of properly colored triangles. So what I'm going to do is I'm going to look at the number of properly colored n simplexes by this coloring. So here we have 3 of them. See, the light blue ones are not properly colored. The dark blue ones are properly colored. But the trick is I'm going to count them by orientation. So if you're a triangle that has positive orientation, that is, if the orientation is the same as the order on the colors, then I'm going to count it as being +1. And if it's the opposite orientation, I'm going to count it as being -1. And now I'm going to take the algebraic sum of these. So here I have 1 minus 1 plus 1 is 1. So despite the fact there are actually 3 of them, I'm going to count it as 1 because the positive and negative orientations cancel each other. So this isn't quite as good as actually counting them, but it's going to have nice combinatorial properties. So in particular, if the content is non-zero, then I know there are properly colored simplexes. So if I add them up by orientation and I have something left over then I must have had something to begin with. Now, the converse is false. If the content is 0, then it could be that I have multiple properly colored simplexes, but they're opposite orientation and they cancel. So counting the simplexes by orientation works in one direction, but not in the other direction. So it's a way of showing that properly colored simplexes exist, but it's no good for showing that they don't exist. So you know, you don't get you can get false negatives. Now something else called the index. So the idea here is the subscript I is a color. So we assume that each of the colors has a number. And so the index with respect to color I is the number of n-1 simplexes on the boundary properly colored by colors other than I. So what does that mean? Well, let's say I is blue. So I'm going to count them by orientation also. So I is blue. So this edge on the boundary is properly colored by yellow and red. And it has a positive orientation. So we'll count that as +1. This one is also properly colored by yellow and red, but the orientation is opposite. So we'll count that as, oh no, that's the same. So we count that, this one, however, is opposite. So this adds 1, that adds 1, and that adds -1. So the index with respect to blue here is going to be 1. Even though there are 3 edges, 2 of them cancel out when we add them up. So this is the same thing. That is, we can deduce the existence of properly colored n-1 simplexes by looking at the index. And, but we can't deduce their absence. So here, the index, say blue is 0. So the index for blue is 1 minus 1 plus 1 is 1. So we have these two quantities, the content, which is the algebraic sum of the properly colored n simplexes, counted by orientation, and the index, which is the algebraic sum of the edges colored by a subset of colors, also counted by orientation. And guess what? They're the same. So the index lemma says.
Just a question.
Yeah.
So this is the on the boundary, or
Only on the boundary.
The boundary is only on the boundary.
Only on the boundary.
So we cancel anyway.
Yeah, they cancel anyway. So in fact, when we do proofs, we actually count the internal ones and then they cancel and so on. But for definitions, I'll just say boundary because it's.
What if you have some edges which are outside?
But then it's not a manifold. So this only works for manifolds with boundary. So it doesn't work for arbitrary manifold, for arbitrary complexes. Yeah. So it has to be a manifold. Okay, so the theorem basically says that the content of this is well, you take the color and you do -1 times the color. It's the index. So we don't need to worry about this -1 term for what we want to do. But in this case, you can check that in fact they're both equal to 1 here.
I was yellow, the other was blue, right?
Yeah.
What is -1 by power?
Oh, so let's say that blue is 0. So I've drawn these as colors, but really the colors are integers from 0 to n plus 1. And so if I is 0, then this is 1. If I is 1, then this would be -1. So when you're dealing with orientation, you have to be careful with the -1s and so on. But if we assign, you say that's 0, that's 1, and that's 2, then you can plug those in here, and then you can check the indexes for the other colors will come out to be the negative of the previous ones.
What's the difference between 0, 1, 2, and 1, 2, 3?
0, 1, 2, and 1, 2, 3?
Yeah, if you call them 1, 2, and 3.
Oh, you have to number them by 0. Otherwise, if you start with 1, then you have to change that. So the colors have to start with 0. So I'm skipping over some of the technical details here. But basically, each of the colors are 0 to n plus 1. And that's the kind of canonical order.
Oh.
And if you go around here, if you run it, if you see them in that order, then that's positive orientation. If you say go around here and that's the opposite order, then that's negative orientation.
So this is the reference order for the
Yeah. So each of these things has two possible orderings, and so you pick one, and then that will determine all of these values. If you pick the other, then everything will be the negative of what it was before. So in all of these arguments about orientation, you start out arbitrarily choosing one of two possible orientations and then pushing through your argument. And if you had chosen the other, then all the numbers would be multiplied by -1, but the equalities would still hold. Yeah, so this is the index lemma, and I'm not going to go through a proof of it. There's a proof in the notes, but it's not too hard to see how you would go about proving it. You start out with one simplex, and then you can say, well, if this simplex is properly colored, then there's only one edge, and you could do the arithmetic and make sure it's oriented the right way. If it's not properly colored, like here, then there's some thing that shows up twice. There's two edges that are properly colored, but they cancel each other out because they have opposite orientations. And you generalize this to n simplexes. And then you argue inductively. You say, well, I have all these things. I'm going to look at all of the edges. The internal ones cancel out. I'm left with the outer ones. And then everything adds up. So it's a fairly straightforward argument. It requires a lot of being careful about -1s and things like that. But it's really just a little bit of symbol pushing. Okay, so you might say, well, that's all very interesting, but we need results about binary values, whereas the index lemma talks about proper colorings. So it's still, it's sort of a poor relation of Sperner's, because it talks about properly colored simplexes, but it doesn't give you quite the same kind of results. So now I'm going to talk about how to translate statements about binary colors into statements about properly colored simplexes. So the basic idea here is that we start out with a protocol complex, and now I'm going to color everything with process IDs. So you have to be careful because we're talking about several different kinds of colorings here. So there's the arbitrary coloring that I gave you before, for which the index lemma applies. There's the black and white coloring, that's the output for the weak symmetry breaking. And this is the coloring given by process ID. So we have a blue process, a red process, and a yellow process. So what I'm going to do now is I'm going to give you, we don't have enough colorings, so I'm going to give you another one. So what I'm going to do is I'm going to look at the binary coloring that we get from the weak symmetry breaking. And you remember white is 0 and blue is 1. And for each vertex here, I'm going to take this binary value and I'm going to add it to the process ID. So here, the original process ID was blue. I add 1 to it, now I get red. So I'm showing you the actual arithmetic on this edge, and then this is the result of all the arithmetic. So here I start out with red, I add 0 to it, I keep red. I have red, I start out with blue, I add 1, I get red, and so on. So I've added either 0 or 1 to each process ID, mod n. So so it cycles around. And now I have a new coloring, which is no longer a proper coloring, except, what happens to simplexes that were monochromatic? That if they were all 0, what happens to them? Well, they don't change. So that if a simplex is all 0, and I add it to a proper coloring, it stays a proper coloring. If the simplex is all 1, then it also stays proper coloring, but I shift the colors around by one in the cycle. So the idea here is that if the derived coloring, if a simplex is properly colored in the derived coloring, then it was monochrome to begin with. So now we've taken a statement about a black and white coloring on a simplex, on a complex that has that's properly colored with process IDs, and I've turned it into a statement about proper coloring for a derived coloring. So now we can use the index lemma to reason about black and white colorings as well as about colored colorings. Okay, so here is the important point that I've been leading up to. That given a black and white coloring, it turns out that the number of, the index lemma implies that the number of monochromatic n simplexes is completely determined by the coloring on the boundary. That if you look at the derived coloring, the content is completely determined by the index. And therefore, when you go to the black and white coloring, it says that the number of monochromatic simplexes is completely determined by what happens here. Now, the interesting thing is...
Parity of, not the parity, but the oriented number.
Yeah, the oriented number, which is... Now, the reason that I've been skipping over so many of these details with the minus ones and so on is that it's going to turn out that we don't actually care what the rule is for determining I don't care what the exact rule is for going from the coloring on the boundary to counting the number of monochromatic things on the interior. All I care is that it's determined. That if I know the boundary, in principle, I can compute what's on the interior, but I don't actually care what that rule is. If I cared what that rule is, I would have gone through the proofs and given you the exact formula. But all we care about now is that, if I know what the boundary is, then that determines the number of chromatic n simplexes on the interior counted by orientation. Now, the trick here is that means that I can take any coloring and go to the interior and recolor it all I want. So here I've got the black and white coloring on the outside, and because I don't care what's on the inside, I've colored it gray. So it could be any color. And choosing different colors for the gray nodes is going to change the number of monochromatic simplexes, but it's not going to change the number counted by orientation. So if I change this, I can change each of these things to black or white, and that will change the number of monochromatic simplexes, clearly. But it's not going to change the number counted by orientation. So yeah, so I could, if I could fill this in such a way that there's one all-white triangle, or I could fill it in so that there's 3 all-white triangles, but 2 of them have opposite orientations, so they cancel when I count them. And no matter how I do this, the actual number will change, but the algebraic sum, the plus and minus 1 sum, is a constant. So if I'm interested...
Fix the boundary.
Yeah, as long as you fix the boundary, you can fill in the interior to anything convenient.
And you can also change the triangulation, the way the interior...
You can change the triangulation, but this is where we beat Sergio at his own game. We don't need to. This is something that they didn't notice. So the proof that this was taken from, what they do is they say, well, there's arbitrarily complicated stuff on the inside. We can rip it out and just put it in a single triangle. But we don't need to do that because we know that we're dealing only with the standard chromatic subdivision. This is what they missed. Is they're trying to do everything with arbitrary subdivisions, which is difficult. But they didn't notice that if there is an algorithm, there's a iterated immediate snapshot algorithm. So we know exactly, we know what complex we're working with. They didn't. So we don't need to change the plumbing. All we need to do is change the coloring. Okay, so it's determined by the boundary. we can color the interior any way that's convenient without changing the sum by orientation. So let's make them all 0. Why do that? Well, this means that every n simplex here has got to intersect one of these interior ones. So if you think of this as being further subdivided, you take every vertex that is not on the boundary and color it white. So every n simplex has got to have at least one vertex that's on the interior. So that means that there are no one monochromatic simplexes at all, because we've colored at least one vertex of every triangle white. So now our life is much simpler, because all we need to do is we can look at the number of all white simplexes on the boundary and count those. So, I mentioned that we have a symmetry here. So what we can do is we can take a, what does this mean? Well, it means that we take a permutation of the process IDs that induces a simplicial map just by replacing each color on a corner with the color induced by the permutation. So permutations basically define maps. And so what we can do is, a permutation that sends green and blue to blue and yellow would map this simplex here. But what I want to argue here is that we can orient, let's arbitrarily pick this simplex and orient it to be +1, since there are two possible orientations. Now notice that each time we can flip it by changing one vertex. So when we change one vertex, we're flipping it over on an edge, and that reverses the orientation. So if this is positive, then this is negative. And so then after k flips, we'll get to the center here. And that will have orientation -1 to the k, for some k. Beg your pardon?
Can you repeat what you are doing now?
Oh, okay. So what I'm doing is I'm interested. What I want to say is that if I have symmetric simplexes here, they have the same orientation.
Symmetric simplexes, and how do you define symmetric?
Oh, so I define symmetric by looking at this. I'm going to pick a permutation here. And remember, anonymity says that if I permute the process IDs and then run the same execution with the process IDs changed, everybody gets the same. You get the same outputs. So that translates into saying that the coloring is symmetric on the boundary of the.
But all simplexes will be symmetric?
So this simplex is symmetric to that simplex under one permutation. So you pick a permutation, and then there's a set of symmetric simplexes. So basically, there's a lot of symmetry here. So in particular, let's look at, if we look at a permutation that say maps this simplex to that simplex, I want to argue that they must have the same orientation. And so what I'm going to do is I'm going to basically do this flip, which goes from positive to negative. And then if I keep going, I'll get from the edge here to the center in k flips, where k is some number. But because it's symmetric, I can do the same sequence. I can apply the permutation to each of the process IDs that I flipped. And I can do a kind of symmetric sweep, replacing each thing with its image. So I do k to get here and k to get here. And so I end up with 2k flips. And since each time I flip, I reverse the orientation. But since I'm doing an even number of flips, I end up with the same orientation.
Symmetry and anonymity still. I mean, so the colors now are what? The inputs, the real IDs, or?
So we're doing weak symmetry breaking.
Okay.
So there's no inputs.
There's no inputs.
And so the colors are process IDs.
Okay.
And so, but what I want to say is that if I have an execution with, here's an execution where green runs first and then followed by blue.
Okay.
So then, but because I'm not allowed to use the fact that it's actually green and blue, if I have another execution where blue runs first and followed by yellow, then this one here has to decide the same as that one there, and this one here has to decide the same as that one there. And so that's what I mean for them to be asymmetric. So formally, we just say, well, we have a permutation, say that maps green to blue and blue to yellow. And that induces a map from this simplex to that simplex. And so that's what I mean to be symmetric. Now, it turns out this is also symmetric with that, and with that, and with that, and so on. So we don't, we sort of have more symmetry than we need. But the claim here is that this is, using an even number of flips, in any dimension, we can get from one symmetric simplex to another one. And so this means this is going to be important when we start counting up the number of monochromatic simplexes. So the basic idea is that if I have symmetric simplexes, they have the same orientation. They don't cancel, they add together. So, so this is basically the closing argument. So how many monochromatic simplexes are there? Well, we know there's no one monochromatic simplexes. There are no all black simplexes because we've taken every internal node and colored it white. So that means that there are only 0 monochromatic simplexes, and the question is how many of them are there? So there's one in the middle. So the central simplex is monochromatic. And without loss of generality, we could say, well, if you run by yourself, you would decide 0. So that means that we can add 1 for this triangle. But by symmetry, we actually have n plus 1 of them. And we know they all have the same orientation. So they don't cancel each other, they add up. And so that says that we get, actually, this should be n plus 1. No, we already counted that. So just these 3 here are n plus 1. So I'm counting them piece by piece. So we count 1 in the middle. So we'll put that in the bin. Now we'll say, what about here? Well, here we have n plus 1 more. So this should be n plus 1, not n. But so here we have 1, which we've already counted. Now we're adding 3 more.
But don't we have to count them as -1 because they have a difference because they share an edge?
They don't. These guys. Well, oh, these guys. Yeah. Actually, if this is plus 1, then these would be -1. Okay. So that should be, instead of plus n, that should be minus quantity n plus 1.
How do you know that this is always the complex photon?
That this is the.
It looks like this.
Oh, actually, we don't know that it looks exactly like this. If this were subdivided, then this triangle would be much smaller. So this picture is schematic rather than, what holds is that we have the corner and then we have a triangle coming out of it. And whatever's connected to has got to be white because we filled in everything. Oh, because here we're looking at one edge and then there's an n minus 1 face here. So there's only one n minus 1 face that contains this. Well, whatever number we have here, we have the same number here.
Same number?
Yeah, because for a symmetry, if we have some number of all 1, here we have only 1.
And then you want to say that it would be odd always?
Yes, so everything here, so here we're looking at triangles or simplexes whose only boundary vertex is at the corner. And so in this picture, there's only 1, but there might be more, but they would cancel, so there would still only be 1 counted. So
orientation.
Yeah, yeah. But the thing is that whatever contribution here, we also get one here and one here, so we get n plus 1 copies of this.
But if it's only two, then they cancel each other every time.
Oh, yeah, but there won't be. Yeah. It's true. Yeah, I'm skipping over sort of the grungy details, but I think the way to think about it is that whatever the contribution is here, it's going to be the same here because the orientations are the same and the same here. So in the general case, let's look at let's say that we have k sub q contribution on one edge, where that could be either positive or negative. So here it's 1, but in fact it's some number k sub q. Now, how many of them are there? Well, this is the number of q-dimensional faces. So you take n plus 1, choose q plus 1. That's the number of q-dimensional faces. So here, if in every simplex. So I have an n simplex, and I look at how many q faces are there. Well, there are this many. So when I subdivide it, I get this many that contributes that many all 0 simplexes. And this number could be positive, negative, or 0. But we know that it's the same everywhere because the orientations are the same, since we're counting by orientation. So what we're doing is we're adding n plus 1 choose q plus 1 times some integer q sub k, k sub q. So each face contributes this much for some value here. And again, we're using the symmetry here that they add up and they don't cancel. Okay, so the total number counted by orientation is this sum here. So we have 1 in the center, and then we have for each face of dimension I, we have this binomial coefficient times some integer k sub I.
If you have more subdivision, you don't just subdivide once, like in the picture, but further subdivisions for then you have more zero monochromatic things in the middle.
Yeah, there's an extra lemma that the 0 monochromatic ones in the middle all cancel out, that the only thing that matters are the ones on the edges. So the Surgeon Armando construction where you rip everything out and put it in a single triangle is, actually they don't cancel out, they add up to 1. But that's I skipped over that lemma.
So all of them cancel out except 1?
Yeah. It adds up to 1. Which is, no, this could be negative. Yeah. Because since we're counting by orientation, we can count things as a negative. Or it could be 0 also. So, but this is the number counted by orientation. So this is a Diophantine equation. And weak symmetry breaking says, well, this is the number of monochromatic simplexes counted by orientation. If it's really a solution to weak symmetry breaking, the actual number is 0. So the number counted by orientation is going to be 0. And in particular, if this is non-zero, then this cannot be a weak symmetry breaking protocol. So the question is, under what circumstances can we guarantee that this number is never 0? Any guesses? Remember your Euclidean algorithm for
I saw the movie.
Right. So that sum cannot be 0 if the binomial coefficients have a common factor. Right? If these are all even, then that can't be 0. If these are all divisible by 3, then that can't be 0. Because if this have a common factor, then you take that modulo of that common factor, you get 1. And that can't be 0. So that's our lower bound.
Why did you use the index lemma? Why did you
Oh, we needed the index lemma to say that the only thing that matters is the coloring on the boundary. That the number of monochromatic n simplexes counted by orientation is completely determined by what happens on the boundary. And because it's determined by what happens on the boundary, we can color everything in the middle to be white. Once everything in the middle is white, then we don't need to worry about one monochromatic simplexes, and we can we can simply look at the number of all white simplexes on the boundary.
again, why can you find this?
Because if I need to worry about all 1 and all 0 monochromatic simplexes, then it's complicated. So the index lemma says that the number of monochromatic simplexes, again counted by orientation, is completely determined by what happens on the boundary.
So if you change something in the middle, it doesn't.
It doesn't change the it doesn't change that. So let's change everything in the middle and make it all white.
See, but then you didn't count using the index lemma.
No, we did. The counting didn't use it. But the thing is that if we by making everything in the middle white, that means that we only need to count the white simplexes on the boundary. And then we can do all this symmetry stuff. If we had to do both white and black things on the boundary, then it would get much more complicated. So this is why I emphasize that we didn't really need to worry about the actual rules for counting. I mean, there's some formulas that say that all white simplexes are counted according to the orientation of the simplex, all black simplexes are -1 to the dimension, and so on. So there's a lot of things you could say about what exactly the count is, but we don't need that here. We can get away with simply saying that.
So you're not using the index lemma for the counting, you're using the index lemma for the recoloring.
Yeah, yeah, that's all that we use it for. But you know, so the index lemma actually gives us a lot more information, but we don't need all of that. So this is okay. So hard renaming is impossible if these numbers are not relatively prime. When does this happen? Well, the n equals 5, that is 6 processes, is the smallest number where this test fails. So if you look at the binomial coefficients for 6, they're relatively prime. And in fact, if n is the product of 2 times a prime, then it also fails. And so what you can show is that there are an infinite number of choices of n for which the test succeeds, and also an infinite number for which it fails. So you know, we've proved this for an infinite number of cases, but we haven't proved the lower bound also for an infinite number of cases. So it's a mixed message. So I guess, so the next question is, well, what about these other cases? What happens when we're going to get out early today?
Oh, you want to go without the break and finish early?
So the question, you know, what's it?
Break.
Okay, okay. Okay, so,
The lower bound.
but I have one more slide. So turns out the bound is tight. So what these guys do is they prove that for all these other things there exists an algorithm. How do they do this? Well, they say suppose that if you count by orientation is 0. So that doesn't mean, as we said before, that there are no monochromatic simplexes. It means that they might be there and they cancel each other out. So what they do is they put on their surgical masks and take a scalpel and they do surgery and they basically push them, they rearrange the complex and push them together until they cancel. And this is not a short or an easy proof. And so, you know, so I'm not going to do that here. And then what you get is you get a subdivision where there are no monochromatic simplexes. And we know from our fundamental theorem for colored tasks that if there is such a subdivision, then there is an algorithm. We have no idea what this algorithm looks like or how complex it is because we're going through several layers of existential proofs. So we have this non-trivial construction to eliminate all the monochromatic simplexes. Then we have this simplicial approximation-based construction for building the algorithm. And all the way through, everything is determined by epsilons and deltas that are pulled out of the air. So we have very little specific information about what the protocol looks like, but we know it exists. Okay, we'll take a break, and then I'll do a very quick wrap-up after that.